Hello everybody, welcome back to my channel. Hope you're having a wonderful day so far. My name is Michael. We are jumping back into Harvard CS50x week 4 on memory. This is part 1 of the lecture.
All right, this is CS50, and this is week 4 on memory, wherein we reveal a topic that's actually fairly distinct to CS50 nowadays as an introductory course known as pointers. Indeed, today is the day you can tell your friends that you learned something about pointers, and in turn, how computers work underneath the hood. I will say that this is the kind of topic, this is the kind of lecture where probably won't all sink in the first time around. Think back to that fire hose that we showed in week 0. In fact, all these years later, I still remember where I was on campus when finally today's topics finally clicked for me. It was in office hours in Elliott House dining hall in the back right-hand corner, which is only to say as you approach this week's material, this week's problem set 4, take comfort in knowing that it is challenging. It's meant to be challenging, but as we sort of ratchet things up and up and up over the past few weeks, we will start to plateau in just about a week, and then it's sort of smooth sailing there on out, even though it might not feel that way initially this week. But this week, we'll focus all the more indeed underneath the hood at like how information is represented, like this here photograph of the bowl of stress balls that we have most every week. But recall that anytime you have an image like this, it of course is composed of pixels, and those pixels or dots each have some bits or bytes associated with them that prescribe what color those dots should be. But there's only a finite amount of information in there. So if we sort of enhance, like you don't actually see the 5, 0 more and more clearly. You only see it larger. And in fact, at this size, you can actually see the dithering, so to speak, which is sort of this cloudiness that looms over the image. And you can kind of see the outlines of the actual pixels. All of those hard vertical and horizontal edges are the pixels, the dots that compose that image. So this is actually an example of, and in fact, on this last slide here, can you see them even most clearly on the screen as we go and go and go? So how do you go about implementing then or representing something like an image? Well, there's bunches of different file formats out there for images. Like there's GIF, there's JPEGs, there's PNGs, and there's others as well. But the simplest of them, like a bitmap image, is literally just a map of bits, horizontally and vertically conceptually. So for instance, here is a grid of bits, 0s and 1s. And suppose, for instance, that maybe 0 represents black and 1 represents white. Can anyone with their human eyes see what this is a picture of, even though it's just 0s and 1s? Can you see it? Yeah. So it is actually a smiley face, because if the 0s are black and the 1s are white, this is what's actually latent in that image. It's hard to see at this size, of course, but if we were to shrink that down and actually use square pixels, black and white, it would probably pop out all the more clearly. Of course, it's not that useful to store things with single pixels, because you can only represent 2 states, like 0 and 1, like black and white. And so here might be that same image actually zoomed in such that you can see all of those individual pixels. But when it comes to color, we of course need more than a single 0 or a single 1 to represent each of those pixels. We probably need like 24, maybe 3 bytes worth for some red, some green, and some blue. And recall that that's in fact one of the ideas we talked about in week 0. How do you go about representing images, for instance? So more generally, this is actually kind of an art nowadays, if only for fun, to actually use small dots and compose things on the screen. And wonderfully, just before we began today, 2 of your classmates bravely volunteered. And in fact, let me invite them to come up and introduce themselves before we reveal what they have made on this canvas here using Post-it notes, square paper, as their pixels.
Hello, my name is Selena. I'm a freshman in Wigglesworth. I'm thinking of studying robotics and possibly in secondary in AFVS.
Welcome.
Hi, I'm Jeffrey. I'm a freshman in Thayer Hall, and I'm thinking about concentrating in Econ and CS.
All right, welcome. And allow me, hang on to the microphone if you would. I'm going to go ahead and reveal what they kindly did on very, very short notice before class began. And here is what they came up with, a grid of pixels, 2 colors here. What is it that we're looking at?
Can you tell what it is? Shall we say? It's,
oh, actually, well, we can ask the audience. What is it they made? Because they're a little insecure about their pixel art. Is that it louder? Again?
A brain, a flamingo?
A flamingo?
Question mark?
Is it a flamingo? No?
No, they said a palm tree on an island.
Oh, it's a palm tree on an island. All right, maybe a round of applause for palm tree on an island if we could. Thank you. There we go. So suffice it to say, when you do have just, thanks very much, if you have just a single color to use, black or white, and you're using 1-bit art, it's actually kind of hard to paint a picture. But if you do have actually more colors at your disposal and an even bigger grid, can you do more interesting things? And so in fact, we invited some past students to do exactly this. We shared a Google spreadsheet whereby we use the cells, instead of as long default rectangles, we just turn them all artificially into squares so that you can use sort of the paint bucket tool and just paint different pixels onto the screen. And among the pieces of art that some of your predecessors came up with were this here, a scene from Mario using a grid of multicolored pixels. This one here of Scratch the cat. This one here in honor of the Harvard-Yale football game coming up in a few weeks' time. This one here using a bit of the same. And in fact, if you'd like to play along at home, just for fun, if you go to cs50.ly/art, you can make a copy in your own Google account of that blank spreadsheet and just play around if you'd like to experiment as well. But this is really meant to motivate one of today's topics, which is indeed how we can start to manipulate data at a lower level, including images and other things. And images, of course, can be, among other ways, be represented with RGB, some amount of red, some amount of green, some amount of blue. Before we dive into that, though, let me augment our vocabulary a bit today by adding another base to our system. So we have binary, of course, which is base 2. We have decimal, of course, which is base 10. Today, we're going to introduce one more, which is useful in today's concepts, as well as others, as we'll see down the line, known as hexadecimal, where you actually have 16 digits at your disposal. And if any of you are artistically inclined, or you might have dabbled in web development, you might actually be familiar with hexadecimal notation itself already. Here, for instance, is a screenshot from Photoshop, whereby if you use the so-called color picker to manually choose a color that you want to paint onto the screen, you see a lot of information over here. But salient to today's conversation is this here, where there's a hash sign and then typically 6 or sometimes 3 digits in this case. 000000 means that the color I'm going to get here is actually black. So it's sort of no red, no green, no blue. Hence the zeros means you're going to get black. Meanwhile, if I play around with the same color picker and I instead do FF, 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 either all caps or in lowercase, I actually get a color that we're going to see today is going to be white, which is like a lot of red, a lot of green, a lot of blue, all the frequencies of light coming together to give us what we know as white light. But now we can kind of play with this, because it's no coincidence that these are indeed 6 digits of sorts, even though they're letters of an alphabet and not numbers yet per se. For instance, FF0000 would seem to mean a lot of red and no green, no blue. And indeed, that's why we get red, according to Photoshop itself. 00FF00 gives no red, a lot of green, no blue. And of course, that's the color Photoshop would give us. And lastly, 0000FF gives us indeed blue, because that's no red, no green, but a lot of blue. So the zeros would seem to make intuitive sense here if you have no red, no green, no blue. But what's with the FF? Like FF, of course, in English are letters of an alphabet, not numbers. Well, it turns out that Photoshop and people in the world of images and people in the world of computer memory tend to use a different system altogether. They don't use binary, and no one really in practice uses binary except the computers we use, because you can't do or see much with zeros and ones alone. We humans in the real world use the decimal system again, 0 through 9, which is just very conventional. But in the context of computers, and specifically memory and files and images, we tend to use hexadecimal, which gives us another 6 digits in our vocabulary. And I'm deliberately calling them digits, even though they appear to be letters, but this is just a convention. We just we want 6 more symbols. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't want to say 10, and I don't want to write 10, because that would be 2 symbols on the screen. So the world years ago decided, all right, when we want to represent 10 with a single digit, let's call it A, and then B for 11, and then C, and then D, and then E, and then F, where F happens to be 15. So this is what's known as hexadecimal notation, and it's really the last of the notations or systems that we'll use. You can use uppercase or lowercase. The software you use kind of decides what convention to use, but they mean one and the same. So hexadecimal, hex implying 16 in this case, otherwise known as base 16. All right, so just a bit of jargon out of the way. How does it actually work mathematically? Like the exact same way as in week 0. The math is a little different. It's not going to come to you intuitively in the same way, but the system is the same. If you've got 2-digit values here, like here are some placeholders, the columns represent the 16ths to the 0th place, the 16th to the 1 place. That math is easy. This is the 1's place. This is the 16's place. Instead of in our human decimal world, 1s, 10s, 100s, or in the binary world, 1, 2, 4, 8. Same idea, just different powers for each of the columns. All right, so this number, 0, 0, represents the number you and I know as 0. In hexadecimal, 0, 1 represents the number you and I know as 1. And it goes from there pretty straightforwardly. 0, 5, 0, 6, 0, 7, 0, 8, 0, 9 translates to exactly what we know in decimal, like the number 9, because it's 1 times 9 plus 16 times 0. Gets a little more interesting when you're using 2 digits, but you're using hexadecimal, because now if I want to count as high as 10 in decimal, I would represent that in hexadecimal as 0a, 0b is 11, 0c, 0d, 0e, 0f, and there's our f. And f, I'll stipulate, just represents the number we know as 15. So 1 times f gives us 15 plus 16 times 0. All right, dot, dot, dot. We're not going to do the whole range of numbers here, but I don't want to call this 10 in hexadecimal, just like in binary. Even though you might see 1, 0, you don't say 10, you would say 1, 0. Same in hexadecimal. So this is 1, 0. But if I translate this pair of digits to decimal, what does this represent? So this is 16, because I've got 16 times 1 plus 1 times 0. And on up and on up and on up. We can sort of do this for quite a while. It gets interesting only once we get to the end. Using hexadecimal, as I've defined it, what's the highest we can count with 2 digits then in hexadecimal? FF would be the highest, because F seems to be the largest digit. So this is actually 16 times 15 plus 1 times 15 actually gives me 255. So that is as high as I can count in hexadecimal from 00 to FF, otherwise known as 0 to 255. And if you don't believe me, quick little math will give us that. Again, 16 times 15 plus 1 times 15 as well. All right, so how is this useful, doing out this math? Well, we have the following why is this useful? So it's very common to use 2 digits of hex, maybe possibly more. Why? Well, it turns out that to represent the numbers 0 through 15, let me spread these apart now just to be deliberate about it. 0 through 15, how many bits do you need? Well, 0, you can use any number of bits. How about 15? Like how many bits do you need to count to 15? So it turns out that it's 4, right? Because in binary, that would be what? The 8's place plus the 4's place plus the 2's place plus the 1, which I think gives me indeed 15. So why is hexadecimal useful? Well, it turns out that you can represent a single hex digit, whether it's 0 or F, using 4 bits, no matter what. And so why do we tend to use 2 hexadecimal digits? Well, it's just useful to be able to describe a single byte, otherwise known as 8 bits, using 2 digits instead of 8. So in binary, we'd have to use 8. In hexadecimal, we can just use 2. And it's just useful visually. Hexadecimal is useful as a result. All right, so when are we going to see this, and why are we going to see hexadecimal? Well, here's like a grid of the computer's memory, just abstracted away as byte, 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 byte in rows and columns. Well, here is how we might number those bytes. As I've stipulated for several weeks now, we could call this byte 0, this byte 1, byte 2, dot, 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 all the way to byte 15. But by convention, we don't use decimal, and we definitely don't use binary. Instead, a computer scientist would think of the addresses, the locations of, the count of bytes in memory as still starting from 0, 1, 2, 3 on up. But as soon as you get to 8, 9, A, B, C, D, E, F. Again, just a convention. There's nothing really intellectually interesting here other than we're using a different base system instead. Here's how the others might play out. And it gets a little confusing because this 1, 0 is not 10 if it's in hexadecimal. But clearly, there's some potential ambiguities here. Like, it's pretty obvious now that if you see an A through F, OK, it's probably hexadecimal. But if you see 10 or 11 or 12, well, it's maybe not. It might not be 10 or 11 or 12. Those might be hexadecimal, even though 1A, 1B is. So this is an ambiguity. And so what we're also going to see today, that the way humans have mitigated this potential ambiguity is when you write things in hexadecimal, by convention, you put a 0x before them. a 0 and typically a lowercase x. That does not mean anything mathematically. It's not an extra 0 per se. It just means to the human reading this, here comes a hexadecimal number. And now there is no ambiguity. So we're going to see a lot of this today. Generally, we won't care about the numbers, but that is what we're going to be looking at, is hexadecimal. So any questions on hexadecimal, which again is just another way of representing numbers?
Wait, I have a question. If anyone can answer this. So he mentioned that you put a 0x is put in front of the hexadecimal, but why was there a hashtag in front of the Photoshop example? Where is that just a representative of what Photoshop declares as? What is the difference between the hashtag that was used in Photoshop to precede the 6-digit code versus the the 0x is put in front? What is the difference between the 0x in front of hexadecimal versus the hashtag? The prefixes 0x and hashtag both indicate hexadecimal notation, but they're used in different contexts. 0x used in programming language like C, Python, and JavaScript to represent hexadecimal numbers. Example, 0xFF, 255 in decimal, and 0x1A3, 419 in decimal. A hashtag used in CSS and design specifies specific hexadecimal colors. A code / way of counting led by a this or a 0x, where the code translates to a specific color within the color spectrum or place in memory. 256 total values, yeah, that's right, base 16, 256 total values, 0 to 255.
OK, so let's see this in practice and start to tease apart what's going on underneath the hood of our computer all of this time when we actually start to use variables and more. So here's a single line of code. Give me an integer called n and initialize it to the value of 50. So fairly straightforward. So let's actually do something with this kind of code. Let me go into VS Code here. Let me go ahead and create a program called, let's call it addresses. .c, because I want to look at the locations in memory, the address of things in memory. And let me stipulate, too, as we've said in the past, just as mailboxes in the real world, houses and buildings in the real world have unique addresses, like we were at 45 Quincy Street, Cambridge, Massachusetts, 02138, USA. Similarly, does your computer's memory have addresses, but they're super simple numbers like 0, 1, 2, ... all the way on up. So I've created a program now called addresses.c. Let's just play around with some familiar code. Let me include standard.io.h. Let me do int main void, so no command line arguments for this. Let me declare that variable n, set it equal to 50. And let's just print out n. So this is like week 1 stuff, super simple and presumably familiar by now, whereby I want to print out, using the %i placeholder, the value there of n. All right, hopefully, if no syntax errors, I can do make addresses, enter. So far, so good. /addresses, enter. And I see, as expected, the number 50. But what's actually going on inside of the computer's memory in this case? Well, we can actually see that over here. Let's look at this grid of memory here. For today's purposes, I don't necessarily know where in the computer's memory at this point the n is going to end up. So let's just arbitrarily say the computer finds room for the int in the bottom right-hand corner of my screen. The size of it is deliberate, because recall that integers tend to be how many bytes on most systems nowadays? 4 bytes by convention, aka 32 bits if you multiply by 8. So who knows? N might very well end up in the bottom right-hand corner of my screen here with the number 50 stored there. Now, it's not literally the number 50. There's literally 32 zeros and ones in the computer's memory that are turned on and off to represent the pattern that gives me the decimal number 50. So again, that's sort of week 1 style stuff, but we're thinking about now the computer's memory. In fact, even though we refer to it as n in my code, it's got to live somewhere. And the address at which it might live, for the sake of discussion, is maybe something notationally written in hexadecimal like 0x123. Completely arbitrary. In practice, it's probably a bigger number than that. But for the sake of discussion, let's assume that that 50, the variable n, just so happened to get placed by the computer at location 0x123. Can we see that in code? We haven't yet, thus far. But if I propose here, maybe going back into VS Code in a moment, maybe we can actually use some slightly new syntax and poke around the contents of the computer's memory. But before we do that, we do need a few new building blocks. And there's not much new syntax today, but we're going to go pretty darn far in terms of capabilities with just a few new symbols. It turns out that in C, if you use the ampersand operator, just one of them, not two. Two means and, logically, just like two vertical bars meant or. If you use just one of them, as we are going to today, that is going to be the so-called address of operator. So you can write ampersand in the name of a variable, and the compiler essentially will tell you where that variable is in the computer's memory. And more technically, when the program is running, you will be told where it is. The star operator, or a single asterisk, is not multiply in this context. It's going to be the dereference operator, which is going to be a trick via which we can have an address and go there, sort of following a breadcrumb, following X marks the spot on a map, and going to that location in memory and just see what's there. Is it an int? Is it a char? Is it a string? Or something else? So these sort of reverse the effects of each other. This tells you the address of something. This tells you how to get to something. So the address of operator and the dereference operator, so to speak. But we need one other building block, and this one's going to be useful in the context of printf. Recall that printf has all those format codes, like %s for string, %i for integer, %f for float. Turns out there's another one, %p, which is going to allow us to print what are called pointers, which are really for now synonymous with addresses in memory. So using just those new building blocks, let me propose that we do the following, leveraging this notion of a pointer. I'm going to change my code in just a moment to still have the same single line here, int n equals 50. But then let's create a second variable called p, just for convenience. But let's declare it as a pointer. A pointer is simply a variable that stores the address of something. So it's a variable that stores the address of something like OX123 or some such value. How do you use it syntactically? It's a little weird, especially since we've used star and the ampersand in other ways already. But you say that I want a variable called p. The type of this variable is going to be a pointer, so to speak. How do you express that? Well, I want it to be the address of an integer. So you say int, but you make clear that it's the address of an integer, not an actual integer per se, by putting a star here. Of all the things we have and we'll see in C, I will concede this is sort of the most confusing way to do this. Ideally, there would just be a variable called pointer, and you just write it, and you get a variable that's a pointer. But in the case of C, you actually specify that this variable p will indeed be an address that points to an integer. So just have to kind of let that ingrain in yourself. This one's a little easier. Ampersand n, how would you express that in English based on my previous definition? The address of n. Ampersand n just means get the address of n. And because code, recall, is generally read and executed right to left in this case, this says wherever n is, get the address of it, like OX123, and assign it to the variable p. What is the variable p? It is a pointer, so to speak. That is the address of an integer. So it is arcane, it's a little weird, but this is kind of as low level as we can get with C, with just telling the computer exactly what we want to do. So let's see this. Let me go back to VS Code here, and quite simply, after clearing my terminal, let me go ahead and print out, using %p, the following address of n. And then we'll enhance this code to actually introduce, actually no, let's do this exactly as I did. Let's go back into VS Code here. Let's declare int star p equals ampersand p, and then print out, not n itself, but print out using %p the value of p itself. So what is this going to do for me? It should print out the address of n. All right, so in my terminal window, make addresses, enter. I messed up because I did something stupid. I forgot the semicolon, as you might have one or more times the past few weeks. Let's do this again. Let's make addresses. Enter. Damn it. I screwed up a second time. I want the address of n, not the address of p. All right, so I'm doing well. So much for remembering this concept from the dining hall of Eliot House. All right, so make addresses. Enter. Oh my God, thank you. All right, so now it works.
Like me.
Hopefully. /
those
addresses.
errors all the
it's not going to be
time.
as simple. in the actual computer is 0x123. It's probably going to be a bigger number. And indeed, it's a much bigger number, but there is an address of some sort. Might be different, run on a different system, but it turns out that the variable n is stored at location 0x7FFEF3C2925C, which is just a really big number that if we did all of the math on paper, pencil, or computer would be a really big decimal number. Why? The server has lots of gigabytes of memory, billions of bytes, so of course it's probably going to be a big number like that. Now, I don't strictly have to create p. And in fact, let me do what my instinct had me doing a moment ago. Let me delete p and simply just print out directly what is the address of n. Let me go ahead and recompile the code, make addresses, /addresses, and I actually do get a different address this time. Why? Because I've run the program again, and things got organized in memory a little bit differently. So these numbers are not going to remain invariant, unchanged, but every time you run the program, things might deliberately or for other reasons get moved around. But all I have done is ask the computer explicitly, what is the address of n? And that's what I'm seeing. All right, so just to recap then what these lines of code are doing, previously when I had both n and p, this latter line is just asking what's the address of n, storing the address thereof in this variable p. But there's some disagreement in the world as to how you should write this syntactically. And just so you've seen it, in case you see a video or a tutorial or a book that disagrees, this is really the conventional way to write the star that means, hey, computer, this is a pointer to an integer, the address of an integer. You could also write it this way, and some people do this. I do think it's a little, this can get you into trouble in certain cases. Some people do this with spaces on either side, which even looks more like multiplication, but it's not. All three will work, but the recommended, the conventional way is indeed to do this, even though I do concede it looks a little weird, but you'll get more and more comfortable over time. All right, so if you're with me that what we've just done amounts to just figuring out where in the computer's memory a variable actually lives, I think we can poke around further to see even more of what's going on. In fact, let me go ahead and propose this. Let me propose here that we go back to VS Code here, clear my terminal window, and let's go back to the version before where I explicitly did have p. So int star p equals ampersand n, and then again, printf, quote unquote, and what I had before was %p\n, comma p. So this printed again, the exact same thing, the address of n. But what if I actually want to print out n itself, just like I did in week 0? Well, in week 0, just like I did in week 1. In week 1, I could have just done, as I did a few minutes ago, this. And this would print out, in the old school way, the value of n. And just as a quick check, make addresses, /addresses, and there's my 50 as expected. But now that I have these two other operators, whereby I have both ampersand and star, I can kind of poke around with them, play around with them in ways that should hopefully, with some practice, make sense. So for instance, I could do this again. Int star p equals the address of n. Well, I could print out n, literally as I'm doing now, or I could use the location of n, called p, and go there with the second of these two operators, the dereference operator. The dereference operator, the single star, means go to this address. And so now, when I go back to VS Code and I do make addresses, /addresses, enter, I still get 50. I'm kind of jumping through hoops proverbially here, because this is sort of the stupid, longer, more complicated way to print out the value of 50. But it just speaks to the relative power that I have by just figuring out what the address is and then going there. But the confusing part, I do think about this, for me and for most folks learning this, is the following. The designers of C decades ago made, I would say, the unfortunate decision to use the star in 2 different ways, and 3 different ways in total. One, multiplication. We saw that in week 1 since. But notice that there's 2 different uses of this star operator. Here, it literally means go there. Dereference the address, that is, follow the breadcrumbs and go there. But when you declare the pointer, when you create the pointer, you also use a star, but you also use the type. So what's confusing, at least to me, is that we're using the star in 2 different ways, both of which are related to addresses, both of which are related to pointers. But when you create a variable or declare a variable for the first time, you specify not only star, but the type of the pointer, just like any other variable declaration. But when you use the pointer subsequently, you do not mention the data type again. The compiler is smart enough to remember, OK, got it. You wanted a pointer to an integer. The compiler will remember that for you. You do not need to remind it. So admittedly confusing, but on line 6, we are declaring the pointer and assigning it a value. And on line 7, we are dereferencing the pointer. So one creates the pointer, one goes to their address. So in terms of what's going on inside of the computer's memory, let me propose that if we revisit the same grid, and we propose that 50 ended up down here, the value n is actually technically at 0x123, what exactly is p, the second variable? Well, I could draw it as follows in my memory. Maybe by chance it ends up here, sort of higher up on my slide. But this is the variable called p. And the value of p is simply literally the address of n. Why is p so big? Well, it turns out on most systems nowadays, pointers, that is addresses, are 64 bits or 8 bytes. So they just use a lot of bits. Why? Well, you and I have gigabytes, again, of memory nowadays. And if you're counting up to the billions of bytes, you actually need more than 4 bytes or 32 bits. Because recall from week 0 even, the highest you can count with 4 bytes or 32 bits is 4 billion, but some of you probably have Macs or PCs that have 5 gigabytes, 6 gigabytes, 8 gigabytes or more of memory nowadays. That means we need 64 bits to count that high, so we can actually label every memory location in order to access these spots. Okay. So what is p? It's just a variable whose value happens to be an address. What is n? Well, it simply happens to be an integer at that address.
The dereference operator is used in language like C and C++ to access the value stored at a memory location that a holder points. Yeah, exactly like word challenge said here.
OK, so how can we now sort of think about this? Well, that is literally what's going on in the computer's memory. But as I just said, rarely do we actually care that it's specifically at 0x123. And in fact, the name pointer kind of conjures up a nice metaphor here. Let's sort of ignore all of the bytes of memory that we're not even using or talking about anyway. And who really cares about 0x123? Let's just abstract that away, as we've done in the past, with literally an arrow when drawing or talking about these things. And just think of p as being a variable that literally points to another location in memory. So indeed, whenever a computer scientist is talking about or arguing about or designing something that involves memory, they're not going to get into the weeds of doing OX anything. They're just going to use arrows to draw things on paper or digitally. And in fact, next week, when these sort of all comes to a head when it comes to memory, we're going to build things in computers' memory known as data structures, fancier structures than simply arrays. We're going to do one-dimensional structures, two-dimensional structures, and we're going to use pointers as sort of a thread with needle to connect this location with this one, then this one, and start to create two-dimensional objects, if you will, inside of our Macs, our PCs, our phone's memory as well.
Whoa, fancy.
So to make this super clear, we actually do have a nice metaphor. Maybe if Yulia wouldn't mind coming up. I keep saying that you can think of addresses in memory as being akin to physical addresses in the real world, like mailboxes for, say, this building. Again, 45 Quincy Street in Cambridge, Massachusetts. And here then is a mailbox that has the name p. So this is appropriate because if a pointer is a variable that stores an address, this here mailbox called p would seem to be, I'll say, storing an address. Meanwhile, Yulia has a separate mailbox here that's actually called n. So it's like a variable in memory. We're kind of cheating because technically the pointer would be twice as big as this mailbox, but Home Depot only has so many different sizes. So they look the same physically. But n, according to the story, lives at address 0x123. So if I am the computer and I am executing code that looks like star p, go to the address stored in p, that's akin to like a person opening up a mailbox, looking inside, seeing that what's in there is not an actual value you care about per se, but it's kind of like a treasure map. X marks the spot, if we sort of abuse the metaphor, which just means if I want to go to the address in p, that means I look in computer's memory, and just to be dramatic, we can do this too. We've got a little big foam finger. This is like the computer pointing at the actual location 0x123, and voila, there is the number 50 that we care about. And for those following along at home, maybe avert your eyes here in Sanders. We can similarly do this with the Yale foam finger as well to dereference that as well. And the crowd went wild for those of you watching from New Haven today with applause. So thank you to the Yulia, though, for this particular demo. Yes, we will. We will enhance the applause in the final version of the video. So let's now revisit, admittedly, a bit of a white lie that we've been telling for a few weeks now. And I kind of tripped over this in week 1, but then sort of waved my hand and solved it real quickly by introducing the CS50 library. But I'm going to propose that we revisit what a string actually is. Now, we used strings in week 1. We then began in week 2 to talk about strings, thank you, as just being an array of characters. So that was the first reveal. But even then, we kept using the word string. But it turns out that strings do not exist in C as a data type. Strings are not a CS50 thing per se, but there is literally no keyword in C called string, string. It's a concept that exists in C, so nothing that we've said over the past few weeks has anything to do with CS50 per se. Almost every programming language you'll encounter in the real world supports strings in some way, but my claim today is that the keyword string is actually made up for us for convenience over the past few weeks. Now, why is that? Well, up until now, we have been creating strings in code with lines like this. String s equals quote unquote hi in all caps semicolon. What that would do, according to week 2's discussion of memory, is it would give us 4 bytes in memory for hi exclamation point and a 4th byte, to be clear, for the null character, NUL, the \0, which is just 0 bytes. And we therefore were able to manipulate that string as though it were an array. So s bracket 0 is the first character. S bracket 3 is the very last character, specifically that null character. Well, really, we can start to think about strings a little differently still today. In fact, let me go back over to VS Code here, clear my terminal window, and let's stop playing around with integers like number 50. And instead, let's do this. Let's give myself a string s equals quote unquote hi exclamation point. And then let's go ahead and print it out, just like in week 1 with %s \n, s. Let me go ahead and increase the size of my terminal window, do make addresses, and here is the very same mistake we glossed over in week 1. Error, use of undeclared identifier string, did you mean standard in? Now, maybe that does sound familiar, but it's kind of a red herring. This has nothing to do with standard in per se. String is undeclared because it doesn't exist in C by default. And in fact, it thinks maybe this is a typo. Standard in is a thing that exists in programming languages, but string, I said, in C does not. But this fix for me, recall in week 1, was to very quickly say, we'll come back to that. And at the top of my code, I went in and added one more include, cs50.h. And somehow, if I clear my terminal, rerun make addresses, that solved everything. And string was brought into existence. But how exactly was that the case? Well, we'll see today what's actually going on underneath that hood as well. So what have I just done with this code? I've simply printed out the string s. But notice, I claim, what's really going on if I visit the actual memory in the computer is, yeah, it's an array. But if an array is just a chunk of contiguous memory, certainly we could figure out what the bytes are, the addresses are of each of those characters, hi exclamation point and the null character. And again, for the sake of simple discussion, suppose the h is at 0x123, stands to reason that I is going to be at 0x124, exclamation points at 0x125, and the null characters at 0x126. The specific numbers don't matter, but what does matter is that they are 1 byte apart. And that is literally what I've meant all these weeks when I say contiguous. Back to back to back, they're literally 1 byte apart. So once we know this, can we sort of leverage this to play around with and see strings perhaps in a somewhat different light? Well, let me go ahead and do this. Let me go back to VS Code here after clearing my terminal. Let's leave string s as is, but let's print out a few different things. Let's actually print out what is inside of s. %p \n is how I can display an address, aka pointer, and let's print out the value of s. Let me go down to my terminal and do make addresses, enter, /addresses, and what I see now is a seemingly random but a much bigger hexadecimal address. So it seems that s is not a string per se, because I literally just told the computer to print it out with printf, albeit using %p instead of %s. But %p just means show me the address of a variable, and it seems that s's technical value is 0x59fb1699d004 4. Now, that is the longer version of what I just proposed for discussion's sake is 0x123. Well, let's be a little more pedantic here. Let me go ahead and print a couple of more things. Let me print out another address using %p, but let me print out the address of the first character in S using my array notation. And then let me do some quick copy paste just to see a few more of these. Let me print out location 1, location 2, and location 3. So we're really kind of making use of this arcane looking syntax today. Lots of %p's, but that just means show me address, 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 and so forth. S bracket 0 is from week 2. Just show me using array notation the first character, the second character, the third, and the fourth. And ampersand is new today. Just means show me the address of that character, not the actual character. So if I go back down to my terminal window, make addresses again, I'm going to see 5 values in total now. /addresses gives me this. Let me zoom in. And what's noteworthy is that the very first one is identical to the second one, which seems to imply that S has the same address as the first character of S. But that sort of makes logical sense, because what else would it be if not the first one? And so what we're seeing here now is a hint that whereas %p is printing out literally the value inside of S, what was %s doing all this time? It was, thanks to printf's implementation decades ago, going to that address and printing character, 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 and stopping only once printf finds what?
The escape operator or whatever.
The \0, the null byte. So some person years ago literally implemented printf. They literally are using S as an address, going to that address somewhere with a star operator in their code, and then using a for loop or a while loop, iterating over character, character, character,
come on,
character
we are getting this. I literally said that.
Until
Let's
it
go.
sees the so-called null character. All of this has sort of been happening for us automatically, but that's really all that's going on. If I go back into the visualization of my computer's memory, here's that same simplification using smaller numbers, 0x123, 124, and so forth. And what is S then when it's declared in memory? Well, it's a pointer, which means it takes up 8 bytes, so I am doing this to scale. But what is S really doing? It's storing the address of the first byte of the actual characters. It's storing nothing else. S is not storing the last byte. It's not storing the length. It's not storing anything other than the first byte's address. But that's OK. Why? Because how does the computer, functions like printf, know where the strings end? Just to be super clear.
The null character.
The \0. That's why we're wasting an extra byte all these weeks, because someone needs to know or tell everyone else where strings actually end. Those of you who do have some prior programming experience in Java or in Python or other languages, you can generally just ask a string, like, what is its length? You can call a length function. You can do .length or similar. Those of you who've done this before, that's because in higher level languages like Java and Python, there is more memory being used than just the address of the variable alone. Someone somewhere is keeping track of the length of that chunk of memory. But C is much lower level. It's much more efficient. It's much more complicated in that it leaves it to someone else, something else, to keep track of where strings actually end. But like, that's it. And in fact, I brought these just to be sort of unduly dramatic. Like, all these weeks, we've had these sort of training wheels on, right? Like, where we've had these simplifications of CS50.h and strings existing, and now we're taking the training wheels off, because like, this is literally all that's been going on since week 1. I'm not sure that added anything. This is all that's been going on since week 1. But again, that's sort of the design of the course, is to help you understand first at a high level so you can just get things working and start playing around. Now we're taking a peek underneath the hood to see what really has been going on all of this time. And indeed, who cares what addresses these things live at? And so the way you would typically think about or draw this on a piece of paper is literally just with an arrow. S is pointing at a chunk of contiguous memory that is null terminated, so to speak. So where did string actually come from? Well, here's how I've been declaring strings today and prior. String S equals quote unquote high. String being supposedly the type of my variable. Well, it turns out that a string we have seen is really just an address. But it's the address of what? Just to be super clear. A string is really the address of
a first
It's first character. So it's first character. So it's first char. So I think the implication of this now is that if we get rid of those training wheels and we get rid of even the CS50 library, we can actually start calling strings char stars. And this is what real geeks call strings, like, oh, a char star in C is known to mean you're just talking about a string, but you're doing it as sort of a lower level actual vernacular, which implies that the address is, in fact, that of its first char. The address of its last char is implicit in that null character that we've been using all of this time. So we've actually seen this kind of before. In fact, just recently we introduced the notion of persons, and I said, well, if we wanted to invent our own data type, and a person, for instance, would have a name and a number, we introduced syntax like this, which was kind of a mouthful, but the only interesting part is what's inside of the data structure in this case. Person was the name we gave to the data type. This whole struct is what we wanted a person to be, and the way we brought a person into existence in C was we defined a type using the type def keyword in C. That's actually going to be the trick to what we've been doing in CS50 for the past few weeks. We're using typedef to define our own type. We want to create an alias, for instance, from one thing to another. So just to keep things simple at first, suppose that I'm really confused by int. Like, it's an integer, I get, but why int? Why int? Suppose I want to create a synonym called integer for ints. I could literally say typedef int integer semicolon. And this will bring into existence a data type called integer, which doesn't really solve a problem other than helping you remember that int is really just short for integer. But the syntax can be as simple as that. It doesn't need to be multiple lines with structures and person attributes like that. So accordingly, how can I define a data type for a string? I can say typedef char star, which is admittedly more mind-bending, but I want to think of it instead as a string. So inside of CS50.h, since week 1, has been literally this line of code. A bunch of other lines too, but this one-liner, because you're including it atop your code, brings into existence the keyword string, but it's just like doing an automatic find and replace between string and char star. That's all that's actually happening really underneath the hood. All right, so let's poke around just a little bit more with these capabilities. In VS Code here, let me propose that we can dabble a little further as by doing something like this. If I go into, let's say, addresses.c one final time, I'm still going to create s as quote unquote hi in all caps. But now, just to be clear, let's print out this string manually, just as we could have back in week 1, except now there is no string, there's only char star. So I'm going to do %c \n quote unquote comma s bracket 0. And then just for the sake of discussion, let me just copy paste this twice so as to print out these two characters. Again, I'm just playing around. In the real world, I should really use a for loop or something like that, but I just want to manually poke around with this new syntax. So let me make addresses again, /addresses, and I should see hi exclamation point 1 per line. So that's just week 1 stuff. But now, let me propose that there's this other feature of C we can avail ourselves of, known lastly as pointer arithmetic. So if every chunk of memory has an address, and that address is just a number, whether it's in hexadecimal, decimal, binary, whatever, they're just numbers, I can actually do math on addresses. And if I can start in one location, I can go 1 byte away, 2 bytes away, 3 bytes away, just by adding 1 or 2 or 3. It stands to reason. So what's the implication of this? Well, it turns out that I don't need to use square bracket notation anymore if I don't want to. We introduced it in week 2. It is a feature of C, and it is a very, very common and useful convention, and probably the convention to keep using. But strictly speaking, we don't need to use square brackets anymore to print out individual elements of an array. For instance, I could change this first line to not be s bracket 0, but I can just say go to the first character of s. Because if s is a string, otherwise now known as a char star, and char star just means the address of a char, well, if I want to print out the actual char, I can use *s to go to that address, and where I will find, X marks the spot, a char in the computer's memory. But here's where the arithmetic comes in. Let me do another line. Printf %c \n, comma, go to s plus 1. So I can literally do a bit of math on my pointer to go one location to the right. I can do this once more. Printf %c \n, comma, star s plus 2 to go 2 locations to the right. And I'm doing this only because I know hi exclamation point gives me 3 locations in total. But if I now do again make addresses, /addresses, I get the exact same behavior. And in fact, the square brackets we introduced in week 2, which again come with C, is just syntactic sugar, so to speak, which is a term of art in computing, which just is a more user-friendly way of expressing this weirder syntax. The square brackets by the compiler are essentially converted into pointer arithmetic for me so that I don't have to write code that admittedly on the screen looks more cryptic than it would with just the simpler, more user-friendly square brackets. But all that those square brackets are doing underneath the hood is effectively pointer arithmetic for you. So if I want to play around one final way with all of this same code, I can even do things that probably aren't the best idea, but do speak to the power of this syntax and this language C. For instance, if I want to print out the actual string s, we know I can do this already, %s, and print out s itself, because s is a string, otherwise known as a char star. So make addresses just gives me hi exclamation point. But what if I only want to print out part of the string? I could start partway in the middle of this thing. What if I do this? Printf %s \n s plus 1. So no star. I don't want to print out a char. I want to print out a whole string. What is a string? A string is an address of the first character of the string, still null terminated. So when I compile this code, printing out, and actually let me get rid of the previous line. When I compile this code with make addresses and I run /addresses, what should I see on the screen now? If I'm not printing starting at s, I'm printing starting at s plus 1.
You should just see I.
Yeah, I think you're saying I, like I exclamation point. Why? Because if these strings start at 0x123 and go 0x124, 0x125, 0x126, and I'm starting at 0x123 plus 1, that means start at the second character. And I think, yep, I now see I exclamation point. If I change it to 2, I now see, after doing make addresses, I think I should just see very excitedly an exclamation point, and that's it. I probably don't want to go even further than this, because then who knows what's going to happen if I start printing beyond the boundaries of the actual string. And that, in fact, is going to be one of the trade-offs here. Even though now, with these simple operators like star and ampersand, we can now manipulate and understand memory at this lower level, we can actually do a lot of damage. And among the things we'll talk about today, too, after the break, is recall the CrowdStrike fiasco a few months back, where like systems around the world broke down, including airlines and the like. That stupid, stupid issue was the result of such a simple problem that, after today's break, you too will understand. But in the meantime, in happier news, let's have some little bites of blueberry muffins in the transit.
I wish I had some of those.
See you in 10.